Welcome to the LEED Platinum Zero Carbon Equipment Selection Submission for the Portable Refrigeration Device Research and Manufacturing Center, engineered by Ferris State University for the 2014 ASHRAE HVAC System Selection Competition. The Ferris design team consists of ASHRAE student members Joshua George, Joshua Snider, Eryk Mancini, and Micah Ringelberg, all of whom are fourth-year seniors in the HVACR Engineering Technology and Energy Management program, with the guidance of Professor Michael Korcal. The project involves the renovation of an existing 31,000 square foot, two-story office and research building located in New York City. This facility will include common spaces such as offices, corridors, and bathrooms, and feature key spaces requiring unique engineering attention such as a clean room and refrigerant research and development laboratories. A traditional engineering approach was taken as a base point, utilizing such standards as ASHRAE Standard 90.1, furthered with special engineering focus placed on the carbon footprint, building synergy, sustainability, and net zero energy. From there, 3 HVAC systems were selected for comparison against the ASHRAE Appendix G baseline system through the use of a selection matrix. The 5 core areas of concern were assigned a point value with a weight factor emphasizing the importance of key criteria of each system. The first system analyzed was the closed-loop water source heat pump system. A major issue for this system is the potential for water leakage over sensitive areas and equipment. When considering geothermal as a source of energy, the New York Department of Environmental Protection sets restrictions and regulations involving city water supply, water tunnels, shafts, and other city resource lines. Avoidance of subway and mass transit tunnels were also taken into consideration. Due to the close proximity to these underground mass transit systems and resource obstacles, geothermal was eliminated as a potential source of energy for the heat pumps. The next 2 systems analyzed were a variable air volume system with reheat and the ASHRAE baseline system, which consists of packaged rooftop units and VAVs with reheat, direct expansion cooling, and fossil fuel hot water boilers. The final and best system choice for this building is a variable refrigerant flow system coupled with dedicated outdoor air units. The variable refrigerant flow system minimizes efficiency losses that conventional HVAC systems typically have. This VRF system will reduce temperature stratification and improve occupant comfort and satisfaction. Furthermore, the system offers features such as reliability, flexibility, maintainability, and sustainability. In addition to the performance and efficiency requirements of the systems, the overall life cycle costs of each system was evaluated. This research and manufacturing center is considered to be a long-life service building and is expected to have a minimum service life of 50 years, as defined by ASHRAE Standard 189.1. With this in mind, both a 25-year and a 50-year life cycle cost analysis were performed. The DOE2 program was utilized to perform accurate calculations. Future anticipated cost in regards to energy, equipment replacement, and operational costs were calculated also. Over the course of 50 years, the VRF system will have the lowest cost of about $8.97 million. Initial costs for the VRF system are high. However, yearly operation provides the best life cycle cost as seen in the graphs. The HVAC system's impact on the environment played a major role throughout the selection process. The main goal was to completely eliminate the use of fossil fuels and to reduce the carbon footprint. The electricity used throughout the building will be obtained from Niagara Falls Hydroelectric Power Plant. This is a local, renewable resource that produces no carbon emissions in the production of energy. Due to the fact that refrigerant is the primary medium of transferring energy, there is no need for harsh chemical treatments that are needed in water-based systems. This avoids having to keep hazardous chemicals within the building and lowers the exposure to building maintenance personnel. Indoor air quality is drastically improved through the use of both basic and advanced filtration systems in the VRF cassettes, as well as the dedicated outdoor air units. ASHRAE Standard 90.1 was utilized to determine the climactic zone that the building is located in, which is 4A. Minimum U values for the floor, walls, and roof were also obtained from this standard, as well as minimum energy efficiency ratings. Occupancy sensors will be used to automatically shut down the system after 30 minutes to save on energy, as the standard suggests. ASHRAE Standard 189.1 was used to enhance the building's overall design performance and exceed the minimum criteria of high-performance green buildings. To ensure that proper ventilation and exhaust rates were provided to each space, ASHRAE Standard 62.1 was utilized to determine the minimum requirements for acceptable indoor air quality. The exhaust rates for the R&D areas were obtained from the owner's specifications regarding the lab hoods within them. Zoning and pressurization played a major role in the design. These two diagrams display both floors and the proper zoning boundaries. Space type, size, orientation, temperature, and humidity requirements were used to determine each zone. Pressure requirements in each zone were dictated by the function of the space. By maintaining the design conditions displayed here in the tables, the occupants will improve their productivity and overall health and comfort. ASHRAE Standard 55 was used in determining the indoor thermal environmental conditions that are acceptable for the majority of human occupancy. The VRF system and the control system were designed to be able to satisfy a wide range of temperature fluctuations that would occur throughout a typical working day. This table displays the design filtration utilized to maintain high indoor air quality. In addition to the primary HVAC system within the building, innovative design was incorporated to further reduce the building's impact on the environment and improve the sustainability of the building as a whole. Many options were considered, but only the most sustainable green options were implemented. A living green screen wall and roof, as well as a high reflectance shingle pathway on the building rooftop, will provide architectural synergy, reduce the heating and cooling loads, and decrease sound levels. This will further reduce the heat island effect considerably and also contributes to securing additional lead points. The donation of the photovoltaic solar panels will be utilized along with a control system that follows the solar inclination to optimize system efficiency. If for any reason the controllers were to fail, the use of solar reflectors will be implemented to ensure direct solar energy hitting the face of the PV panels. It was determined that if the photovoltaic solar panels were installed on the entire available roof area, they would be able to generate enough power to offset 92.35% of the building's total electrical load. Through the implementation of these solar panels, the cost per square foot is $3.20. This is approximately $196 less than the $200 maximum set by the owner's requirements. Reducing the building's water consumption was another key aspect of the design that was taken into consideration. A perforated parking lot with underground collection tanks will serve as a rainwater collection system to help offset the water usage of such things as boilers, irrigation for the landscaping, and the green roof. The parking lot itself is made up of a white, highly reflective colored asphalt to further reduce the heat island effect. A condensate recovery system will collect water from the cooling coils of the HVAC units and then be piped to a collection tank where it is filtered and treated for use in the Dolphin water treatment system. Electric lighting accounts for 20% of the total primary energy that is consumed by commercial buildings. With this in mind, daylight harvesting was implemented. Through the use of an automatic daylight responsive control system, drastic energy savings can be obtained as displayed here. Through obtaining green power from Niagara Falls, in conjunction with these solar panels and the energy-reducing methods previously discussed, this building will achieve a zero-carbon footprint. When selecting HVAC systems and equipment for the center, careful consideration was given to how chosen systems would affect the overall appearance of the building and how it would fit in with its surroundings. The ducted VRF cassettes will be located above the drop ceiling in order to reduce system visibility, hide piping and ductwork, and decrease sound levels. The diffusers will provide an air curtain along exterior walls as well as maintain an aesthetically pleasing appearance. Mechanical equipment located on the roof will be hidden by the living green screen wall. This wall blends in with the natural landscape of the area and increases the visual aesthetics of the building as well as reducing equipment audibility. The boilers and associated equipment are located in the mechanical room, which will keep them out of sight and maintain the overall look of the interior architecture. Lastly, the underground rainwater collection system will have no effect on the exterior appearance of the building. LEED, or the Leadership in Energy and Environmental Design, is a rating system designed for green buildings created by the U.S. Green Building Council. It involves 4 levels of certification ranging from certified to platinum. In order to achieve the level of certification desired, specific criteria must be met. For this particular building, LEED Platinum was attained with a score of 104 out of 110, based on the LEED version 4EB O&M score sheet. Key factors that allowed for such a score were having occupants utilize public transportation such as subways, installation of a building automation system that monitors and controls all building systems, and low-impact development such as solar collection, gray water collection, and outdoor air quality control. The Portable Refrigeration Device Research and Manufacturing Center contains some very unique spaces that were taken into careful consideration. These unique spaces include a clean room and 4 research and development laboratories that require specific temperature and humidity levels. The system selected for the clean room was a packaged modular air handler that is located in the adjacent R&D space. This custom air handler will help to meet the strict temperature, humidity, and filtration requirements and incorporate an advanced control system to maintain these levels. The R&D areas also require their own process cooling water system. This process water is chilled through a ground loop configuration and then filtered to be used again in any water-cooled equipment within the laboratories. There are also multiple lab hoods within each R&D area that incorporate variable frequency drives and rapid response dampers on each exhaust fan. The exhaust fans selected for these hoods were high-velocity, high-throw exhaust fans that ensure contaminants being exhausted can be diluted to a less harmful level. Perforated ceiling tile comprised of 52% recycled material is utilized in the clean room and R&D areas to even out air distribution and control sound levels. By using low-impact development practices such as the biowall to reduce the heat island effect, on-site and off-site renewable energy, a gray water collection system for building water use reduction, and daylight harvesting for reduced electrical consumption, a truly sustainable building is possible with the implementation of a complete variable refrigerant flow system. The VRF system selected provides large improvements in energy efficiency and total life cycle cost, as well as creative green design, making this system the preferred choice to meet owner requirements and set new standards in building design. In conclusion, by referencing ASHRAE standards, journals, and handbooks, along with reputable online sources, the design team was able to produce an extremely energy efficient and environmentally responsible final building system. Through the use of ASHRAE Standard 189.1, the design team was able to produce a building above and beyond normal design practices for high-performance green buildings. Thank you for watching Ferris State University's presentation for the ASHRAE 2014 Student HVAC System Selection Competition.